Hello, and thank you for joining me for this Petra MAX webinar on measuring chlorine and catalyst by XRF and UOP 979 precision compliance. In today's presentation, we'll discuss catalyst sample preparation and measurement by XRF, specifically on the Petra MAX analyzer. However, whether it's by Petra MAX or other XRF techniques, sample preparation is critical for good analysis. Additionally, I'll cover Petra MAX compliance to UOP 979 precision by reviewing data from a single laboratory 2-analyzer experiment. While UOP 979 is traditionally a WD-XRF method, we'll discuss how ED-XRF analyzers, such as the Petra MAX, may be a suitable alternative to WD analyzers. First, let's discuss sample preparation. Unlike finished fuel products, catalyst is non-homogeneous. When you consider the small spot size of the Petra versus the large size of catalyst particles, this may lead to inaccurate and imprecise results if the best practices in this webinar are not followed. Key takeaways include grinding the samples prior to analysis. Less than 325 mesh is recommended. Tapping the sample cup prior to analysis will compress the ground catalyst powder. Measure multiple focal points on the sample and report the average results. For the autosampler, measure samples one at a time and use a vent clip to keep the sample cup in the correct orientation in the autosampler slide. Now we'll go into each of these points in more detail. Precision is dependent on particle size. The smaller the catalyst particles, the more homogeneous the sample, and the more precise and accurate the measurement will be. So how small is small enough? UOP 979 requires that the samples be ground to less than 325 mesh, which is about a 40 micron particle size. This will require a laboratory grinder. For comparison, a coffee mill is capable of grinding to less than 80 mesh, which is about 177 microns. If you look at the picture on the right, you can see an 80 mesh screen on the left and a 325 mesh screen on the right. 325 mesh is so fine, it is practically impossible to reach this particle size by hand grinding with a mortar and pestle. So hand grinding is not recommended. That being said, however, grinding the sample using any means is better than not grinding the sample at all. Next, we will review a couple of best practices that are helpful in any case, but are especially important if the user is not able to grind the sample to the recommended 325 mesh. The first of these two practices is simple. Make sure to tap the filled sample cup on its side to compress the ground catalyst powder. This will help present a more homogeneous surface at the focal point. As you can see in the pictures, the compact samples in the bottom two pictures are more homogeneous than the untapped samples on the top. Also, remember what I said in the last slide about this best practice being especially important for coarsely ground samples? If you take another look at these pictures, you can see that the sample on the left is more coarsely ground than the sample on the right. Note that tapping the coarsely ground sample makes a huge difference in sample presentation as compared to tapping the more finely ground sample on the right. Note that tapping a more coarsely ground sample will not replace the 325 mesh recommendation, but it is a very useful tool for those who do not have a laboratory grinder. One last note. When filling the sample cups with catalyst powder, you'll want to fill the cup so it is at least 3/4 full, so that when you turn the cup on its side and tap, it will be at least half full of compressed powder. The second best practice that is especially important for coarsely ground samples is to look at multiple focal points on a sample and use the average of these determinations as the measurement result. To do this, follow the previous outlined best practices to make a catalyst sample. Tap the cup on its side and measure for 100 seconds on the Petra MAX. After measurement, remove the sample, shake to mix the powder, and then re-tap the sample to compact and make the sample focal point more homogeneous, and measure again for 100 seconds. Follow this procedure again to obtain a third determination, and then average the results of the 3 determinations in order to obtain one measurement result. In order to get a proper result, this will require 3 separate measurements of the sample. It is not suitable to do 3 100-second repeats using the repeat function of the Petra, as this will only look at one focal point. While it is true that 3 repeat measurements using the same focal point will be more precise than 3 separate measurements, it may not be an accurate representation of the chlorine content in the sample. The goal here is to obtain an accurate representation of what's in the sample. So do not take a shortcut and use the repeat function on the analyzer. Remember, if it's important enough to do this measurement, it's important enough to do it correctly. In order to best measure samples in the Petra autosampler, it is recommended to measure compacted samples one at a time using a vent clip. Place the vent clip on the top side of the filled sample cup in the 12 o'clock position, and then tap the cup to compact the powder in the bottom half of the cup towards the 6 o'clock position. Place the sample into the autosampler slide with the clip upwards as directed in the picture on the right. When placed in the autosampler slide, the vent clip catches on a groove in the slide, which orients the sample correctly before it drops into the measurement chamber. For best results, place each new sample in the autosampler slide when the previous sample has dropped into the measurement chamber for analysis. Yes, that's right. When running powdered samples on the autosampler, it's best to run them one at a time. Why is this? Let's take a look at the next slide. This picture shows the bottom of the autosampler slide, which is normally inserted into the Petra. The vent clip groove that runs down the center of the autosampler slide is a wide groove at the top of the slide, which narrows to a tight fit at the bottom of the slide, shown here in red. While this groove will keep a sample from spinning 90 degrees at the top of the slide, it won't stop a powdered sample from being jostled around in the slide if it's loaded with multiple powdered samples. Now that we know how to run powdered catalyst samples by XRF, let's discuss UOP 979, which is a test method for total chloride in alumina-supported catalyst by WD-XRF. This method is for fresh, regenerated, and spent alumina catalyst samples in the range of 0.01 to 3 mass percent. If you look at the notes section of the test method, you'll see the section on EDXRF analyzers. Note 3 of the method states that EDXRF may be a suitable alternative technique, but that it is up to the user to ensure that the EDXRF instrument meets the precision criteria in this method. For those of you who are not already familiar with the Petra MAX, it is a type of monochromatic excitation EDXRF, commonly known as HDXRF. This is a question we commonly get asked, so I wanted to stop and clarify that HDXRF is EDXRF. Now, on to UOP precision. This is how the UOP precision is presented in the method. It is a bit confusing to decipher, especially if you have an EDXRF instrument that is not capable of running at the high 1, 2.4, and 4 kilowatt power that the WD-XRF analyzers used to determine method precision. So how do you know if your instrument is precision compliant? According to the UOP method, analyses should not differ by more than the allowable differences shown in the table with 95% confidence. So, if we first look at repeatability, which is in orange, remember this is the same laboratory, same analyst, same day, the highest allowable difference between two spent samples measurements is 0.03%. For regenerated catalyst, it's 0.09%, and for fresh, it is 0.02%. For site precision in blue, which is the same laboratory, different analyst, and different day, the highest allowable difference between two spent sample measurements is 0.05%. For regenerated catalyst, it is 0.11%, and for fresh, it is 0.03%. Measurements that are less than or equal to these values in orange and blue would be considered precision compliant. However, let's also consider optimal performance. That is, performing better than the test method. The precision of the UOP test method was determined in a study using 3 WD-XRF analyzers, all listed in this table. And if compliance is being less than or equal to the highest allowable difference, then optimal performance is achieved when you are less than the lowest allowable difference. For repeatability, in orange, this is when the difference between two samples is less than 0.02% for spent samples and less than 0.06% for regenerated samples. For fresh samples, as we only have one data point, the highest and lowest differences are the same. For site precision in blue, this occurs when the difference between two samples is less than 0.03% for spent and 0.09% for regenerated catalyst. I want you to keep an eye on these values, because these are the values that we'll be comparing our Petra MAX data to later. 0.02% and 0.03% for the spent samples, and 0.06 and 0.09% for regenerated. Now let's move on to our experiment. For our experiment, we used a nested design similar to the UOP method performance study, wherein we measured 2 spent samples and 2 regenerated samples, as no fresh catalyst was available. These samples were measured twice each over 2 consecutive days using 2 Petra MAX analyzers run in one laboratory by one analyst. Got that? It may also be helpful to think of it like this. The 4 catalyst samples were run 8 times each over a period of 2 days for a total of 32 test results, using the best practices described earlier in this webinar, which means that the measurement result for each circle in this diagram is the average of 3 100-second determinations wherein the sample was removed from the analyzer, shaken, and retapped between determinations. If you want the best results for chlorine and catalyst measurements, it's important to follow the best practices outlined earlier in this webinar. Now, on to the experimental results. Here is the testing data. Let me start with the results summary, and then I'll show you how I got there. Petra MAX is compliant with UOP 979 precision. For the spent data, Analyzer 1 performed better than the UOP 979 precision, that is, lower than the lowest difference. And Analyzer 2 met the method precision. For regenerated samples, both analyzers performed better than the optimal UOP 979 precision. Now, let's get into some details. Here are the 4 catalyst samples, 2 spent and 2 regenerated. Here are the 16 test results from day 1, where each sample has been measured twice on 2 analyzers. And here are the 16 results from day 2. These 2 arrows represent the repeatability difference for each pair of measurements on day 1 and day 2 respectively. If you remember, the optimal repeatability difference should be less than 0.02% for spent samples. According to our results, day 2, analyzer 2, spent sample 1 repeatability difference is 0.02%, as indicated in the highlighted box. But everything else is less than this, which indicates that the Petra MAX repeatability for spent samples is UOP 979 precision compliant or better. If we now take a look at the optimal repeatability difference for regenerated samples, it should be less than 0.06%. And in fact, it is much less than this, indicating that Petra MAX repeatability for regenerated samples is better than UOP 979 precision. Now let's take a look at site precision. These 4 within-lab differences represent the differences between these measurements and these measurements. This is site precision. Same sample, same laboratory, but analyzed on different days. So optimal site precision differences for spent samples should be less than 0.03%. And it is, for every site precision difference except these 2 combinations highlighted in yellow, which indicates Petra MAX site precision for spent samples is UOP 979 precision compliant or better. For regenerated samples, optimal site precision differences should be less than 0.09%. For Petra MAX, all site precision difference combinations were much less than that, which indicates site precision for regenerated samples is better than UOP 979 precision. Again, to summarize, Petra MAX is compliant with UOP 979 precision, and in some cases, it actually performs better. Before we finish up, keep in mind these key takeaways. Samples must be ground prior to analysis. The smaller the catalyst particles, the more precise the measurement. Tapping the cup prior to sample measurement compacts the sample and presents a more homogeneous surface at the focal point. Measure multiple focal points on a sample and report the average of these determinations as a single measurement result. Remember, these must be separate measurements. Do not use the repeat function on the Petra. Use event clip and single sample analysis for best results on the autosampler. And lastly, Petra MAX complies with UOP 979 precision, and in some cases, performing better than the method. Thank you for joining me for today's webinar. If you would like more information, please visit the resource library at xos.com and download the Reliable Solution to Measure Chlorine in Catalyst by UOP 979 white paper. Thank you and have a nice day.